This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is turbine efficiency. In this example, we're given a turbine that produces 3,000 horsepower from steam. We're told the inlet state is 800 psia and 1,000 Fahrenheit, and the flow rate of steam is 20,000 pounds per hour. That's a good-sized turbine. The exit pressure is 2 psia. We're asked to find the maximum power and the turbine efficiency. Now, the maximum power from a device comes from a perfect device. And we define a perfect device in thermodynamics as an isentropic device. So W dot for delta S equals 0 is perfection. To compute the work rate for a turbine is the mass flow rate times the enthalpy change, H1 minus H2. So we're going to need that information. But what I want to do is to think about this turbine, which is, I'll say this is the actual turbine, and I want to think about comparing that to another turbine that's ideal. So let me quickly sketch out another turbine. And I want to have the same inlet state, P1 and T1. So I want to make that the same as these. I want to have the same exit pressure, 2 psia, but I want it's a different state because these are different devices, and the final state is going to be with an enthalpy H2S and an entropy S2S. So the final state we're going to seek is really state 2S. Okay, and it's isentropic, so we know that S1 is equal to S2S. And we can look up state 1 and get started. And state 1 is superheat. So let's go find state 1 and get some values at this 800 psia and 1,000 Fahrenheit. We need a superheat table. Here's a superheat table, superheated water. It starts out at 1 psia. It goes up to 100. That's not high enough. We need 800. Here's page 2. Goes up to 300. That's not high enough. Here's page 3. 800 is here. So this is the corner of the table that we need. Temperature is in this column, enthalpy here, and entropy there. So let's pull out those values. At the appropriate temperature is 1,000 Fahrenheit. The enthalpy is 1512.2, and the entropy is 1.6812. Let me transfer those to the other document here. So we're going to say H1 is 1512.2, and that's in BTUs per pound mass. And S1 is 1.6812, and that's in BTUs per pound mass per Rankine. And that's the same as S2S. S2S. All right, so that tells us we've got state 1. We're going to find state 2 from two pieces of information. One is that we know the the entropy already, and we know the final pressure. So state 2 is at 2 psia, and it's a mixture condition. So let's go to a mixture table, and we're looking for, to get the work up here, look at the work rate, we're looking for H2S. So we're going to find that as follows. We're going to say that that's equal to, let me erase that, we're going to say it's equal to, by the lever rule, HF plus X2S times HFG. So we need to find the quality at condition S. And then we're going to use the enthalpy that we know. I'm sorry, I'll get it. We're going to use the entropy that we know. This is the same as S2S, also with the lever rule, but now it's going to be S sub F plus X2S plus SFG. And we're going to solve for X2S to be S S2S, the value that we know already, minus SF from the table, divided by SFG from the table. So let's go get some table values and fill out this expression. So we need to go back to the table, and at 2 psia would be the mixture, the pressure table. That's where we're going now. So we'll be back up here and find a saturated pressure table for water, and we need 2 psia. We're going to come in here finding values on entropy. We're going to get S sub F, the liquid value, is 0.175, and the difference between the vapor and the liquid value is 1.7448. Those are what we need for the lever rule calculation. So coming back, I'm going to have the known value S2S is 1.6812. The liquid value SF is 0.175, and SFG is 1.7448. When I calculate that, I get 0.863. That's the quality. That's the mass percentage of vapor present. And then I can use that to get the enthalpy with some table values. H2S is going to be, well, let's go find some appropriate values from the table. We need HF and HFG, same pressure table, same pressure 2 psia, but now we're going to look under enthalpy and find that HF is 94.02, and the difference between the vapor and the liquid is 1022.1. Transferring those back, we're going to calculate using this relationship. HF is 94.02. The quality is 0.863. HFG is 1022.1. And when I calculate that, I get 976, and it's in BTUs per pound mass. All right, we're still working on part A. What's the maximum work? Well, we need this expression. W dot, I'll say maximum, is going to be the mass flow rate. We're given 20,000 pounds per hour. H1 we looked up was 1512.2. H2S for the we're looking at the ideal device was 976, and when I calculated that, I get 1.072 times 10 to the 7th BTUs per hour. I'm going to convert that though to 4,211 horsepower. So that's my answer to part A. That's the ideal, the maximum possible power for an isentropic or perfect device. All right, part B says, what's the efficiency? And here's the definition of the efficiency for a turbine. We have the actual over the ideal. This is appropriate. There's a different definition for a pump or a compressor. For a turbine, it's actual over ideal. And we know both these values now. The actual, we were told, was 3,000 horsepower. And of course, that's why I converted to horsepower. The ideal was 4,211 horsepower. An ideal turbine produces more work than an actual one. And this value, when I crunch it, is 0.712, or 71.2%. That's a modest efficiency. Modern, highly engineered devices can expect the efficiency approaching 90%. Turbines, steam turbines, have been carefully and assiduously engineered for 100 years. Let's recap. In this example, we are given an actual turbine and an inlet condition and exit pressure and its work, and we're asked to find the maximum work. To study the maximum work, we look at an ideal device with the same inlet conditions, the same exit pressure, and a different exit condition, an ideal exit condition, identified by isentropic. We use the lever rule for enthalpy to find the final value, and on the way we had to find the quality from the known enthalpy. we found that the actual work was lower than the ideal work. The efficiency is defined to be a ratio, in the case of a turbine, of the actual divided by the isentropic work, and efficiency always is less than 1. Now, other philosophies will tell you that human devices fall short, but thermodynamics can tell us how far human devices fall short from ideal behavior. And if you understand this central tenet of thermodynamics, then all will be well.